Welcome. Today we talk about line integrals. We have already seen the concept of a vector field last time, and we have fx, y. So these are two functions, p, q. And let's take a simple example like minus y 0. So what this means, this 0 means that there is no vertical component, there are only horizontal components, and as bigger y is, as more it goes right to the left. This vector field looks like this. And on this side it would go like that. So, and then what we have new now is also a curve. We have also, this is a vector field. And then we have a curve, r of t. So this is x of t, y of t. And let's also assume we have a simple curve like cosine t. Let's take 2 plus sine t. So in this case, this is 1, this is 2, so it is a circle. So this is the circle curve. And so imagine that would be a bird going, flying here on a circle. Maybe this is the water here, and this is wind. We have seen last time the interpretation of wind. So wind produces a force, and what we do, we think about this F now as a force. And this is some path of some object like a bird. So that's our bird here. Flying around. Bird. Seagull flying around here. And now we want to see how much energy it gains, how much work is done on this bird. And so what we have is, when we have a force and we have a velocity r prime, so f of r of t, that's the force at r of t, so that's r of t. So we have a force here, which is the yellow thing, force, and then we have also a velocity, and then r prime t. So force times velocity from physics, you know that's power. Force times velocity is equal to power. So as more force you do on something, as more power you use, and also as faster as you do, as more power you use. And then that's not yet energy. Energy is when you integrate it over time, and that's what we do. Think about t as time here, and then from a to b, that's dt. That's what we call the line integral. This is a line integral. Let me just abbreviate it. We just say over the curve we take f dr. So that's a shorthand notation for this, and that's called the line integral of f along r. So it has the interpretation as work or energy. So this is work, energy. And so this machine here, for example, produces some energy. Every time there's a force acting. I explained this a little bit. And we have this. But that's the definition of that's the important definition of what we are looking at. So we have two things. We have a curve and we have a field, and we are kind of combined. They are both independent from each other. There's no relation here, and we want to see how much energy we get. In this case, we can compute it. Let's just do it. So in this example, what we do is if the bird goes once around here, around the circle, so we integrate from 0 to 2 pi. Now f of r of t, we just plug in here we plug in the x and y. So we plug in here the vector field, which is -2 minus sinus t, 0, and we dot it with a velocity. So r prime is minus sinus t cosine t. So that's how we compute this. That's how we compute this line integral. Let's just take the dot product here. So this is the integral from 0 to 2 pi. Then we have -2 plus 2 times sinus t plus sine square t plus 0. So that we can integrate this. This is minus cosine t from 0 to 2 pi. And then plus the integral from 0 to 2 pi sine square t, which is 1 minus cosine 2t half. And so that's 0 here, because at both points it's the same. And then plus t half plus sinus 2t fourth from 0 to 2 pi. And that gives us just pi. So the work done by this, the work done on this bird, going around once in a loop, is pi. So this bird has gained energy by going around like that, and that's what birds actually do. So the wind is usually lower near the water than further up, and so you can use this to gain energy. So this is an important moment, because we generalize the fundamental theorem of calculus now to first time to higher dimensions. And what we have is we have a curve parameterized. So this is a curve r of t, and maybe this is r of a, and this is r of b. And we have a special case of a vector field which is a gradient field. We talked about this last time. So we have f is now a gradient field. So that's a special situation. And you can think about it like that, right? So we have the level curves of f, maybe they are somehow like that. So this is f is equal to constant. And then the vector field is perpendicular to it. So the vector field is gradient field. Maybe it's something like that. So that's f. So it's a gradient field. And now there is some magic going on now. We don't actually have to do that integral. What we have is the following theorem. So if we integrate from a to b, this line integral, we take the line integral of this f, r of t, r prime t dt. So the work done with this gradient vector field is nothing else than f of r of b minus f of r of a. Very important theorem, fundamental theorem of line integrals. I just abbreviate it as FLTY. Fundamental theorem of line integrals. You will hear that a lot more. So that's, let me just make it a little bit stand out here. Very important thing. Let me just tell you what it means. So in this case it means that we can, instead of computing the work, so the work is equal to the potential energy difference So in this case, if this level the function has some value here, the value here, that's really the only thing what matters. So it doesn't also matter what the curve is. It just what matters is only the endpoints. So what are a consequence? Before we look at an example, what are the consequences? Is so if r of t is a closed curve, Then this line integral, which we just abbreviated as the integral c f dr, this line integral here is 0. And f is the gradient field. Then the integral along the curve, so this is a curve, closed curve C, then the gradient f dr is equal to 0. Some old-fashioned notation makes here a circle around to kind of indicate that this is really a closed curve, but that means that in a gradient field, we cannot gain energy. So this is vector field here. We cannot gain energy in a gradient field. So the example of the bird before was actually an example where we gained energy when we went around a circle. That was not the gradient field. So the example here, f is equal to minus y0, was not the gradient field. And indeed, if you check the qx minus py, that was this Clairaut test, is not 0. That's equal to 1. That's not equal to 0. So the Clairaut test fails, and so it's not the gradient field. But we see it also when looking at the line integral. But it's a pretty cool theorem because it allows us to actually compute these line integrals very conveniently if you have a gradient, if you have a potential. Let me just show you an example. Oh, before we do that, I want to actually prove it. We have to prove that. It's very important. But it's a one-line proof. It's actually, there's almost nothing to do. It's actually, maybe you see it already. What is the proof? Show me the proof. The proof is very simple. Because we remember, that's one of the reasons why we look at this. So what is this? Actually, we don't even have to write almost anything here. What is the gradient of f of r of t? If you look at that, that's just by the chain rule, that's just the d over dt. So what we have is we actually integrate a derivative of a function. Maybe this is g of t. And then we evaluate g at b and minus g of a. So now if we integrate that, just show you that, we integrate this, integrate from a to b, then by the fundamental theorem of calculus, we get f of r of b minus f of r of a. QED. So there are two things which come here in. One is the chain rule. That's one reason why we have the chain rule. And the second is the fundamental theorem of calculus. And this is a first generalization of the fundamental theorem of calculus. So let's look at an example of a problem. We can make wild examples and solve them relatively easily. So what we have is we have a curve here, t sinus to the 77t. So that's kind of, put the bracket there. It's an insane integral to do if you actually want to do the integral, but we don't want to do that integral. So what we have is we have a curve, and that curve is actually something like that. It's kind of like, it's like sinus, it's something like that. The curve is kind of doing something like that. And then at pi, we are here. We are at r of pi is actually just pi 0. So we start at 0, 0, which is r of 0, and we end up at r of pi. So if you wanted to compute the line integral, that would be very hard. would be hard. So what we suspect is that this is a gradient field, and indeed this is a gradient field. If this is P and this is Q, remind you how we actually find. We can find a potential. Meaning that f is the gradient of f. And so what we have to do is we have to integrate this with respect to x. So f is equal to x cubed third plus xy plus x squared y and plus a constant which depends on y. And then we compute fy, which is equal to x plus x squared plus c prime y, and compare it with what we have here, which is y to the fourth plus x squared. And now what we have is the magic is happening. That's the cleral that actually goes away here. And so we have a c prime is y to the fourth, and so c of y is equal to y to the 5/5. So what we have is we have actually our function. Let me just write it down. So let me write this down. C of y is y to the 5/5. And so we have our function f of x and y is x cubed third plus xy plus x squared y plus y to the 5/5. Now, in order to solve this problem, we don't compute this integral, but we just evaluate by the fundamental theorem of line integrals. We just have to evaluate f pi 0 minus f 0, 0. So f pi 0 is pi to the 3/3. The rest is 0, so this is pi to the 3/3. And the line integral would be completely insane to compute, because you look at this integral, we would have to do here 77, but cosine 77t, and then kind of put that into y, and then integrate, and then we would have to do integration by parts and all kind of things. That's the only example which I'm doing here, because we have not so much time for this lecture. Next week will be more. Now we have seen that if you have a gradient field and we go along a closed loop, that we don't gain any energy. So we have one of the consequences of the fundamental theorem of line integrals is this f of r of b minus f of r of a is 0 if r of a is equal to r of b. And that's called the closed loop property. And we can write it maybe like that, f dr is equal to 0. So let me just make this green. Closed loop property. That's actually equivalent to the, we only have seen this direction, but we will see it next week, that this is actually equivalent here. And then we have another property which is called path independence. So what it means is if you have two, let me just make a picture here. We have a closed loop, we get 0. If you have a point A and a point B, and we have one path R1 and a path R2, or C1 and C2, then what we have is that the line integral along C1 FDR is the line integral C2 FDR. Okay, let's make that yellow. Actually, why not red? Path independence. Also, this is a consequence of the fundamental theorem of line integrals, because we have f of r of b minus f of r of a. It doesn't matter which path we take. So this is also, it turns out this is also equivalent, and you can see it best with, this is equivalent because you build a closed loop by going first around this and then going backwards here. So the work done here minus the work done here is 0, which means the work done here plus the work done here is the same. So these are all equivalent, and that's what one calls conservative. So conservative is kind of like an umbrella name, but they're all equivalent. This is always equivalent. This is theorem. Now there is another property which we have seen. If you have a gradient field, that the qx minus py is equal to 0. And this is called irrotational. Now it turns out that I mean, if you have a gradient field, then this is the case. This is we know that, right? That's what we have seen. If we have fx, that's Claro. Claro tells us that this works. But there is. Let me just make this yellow. But there is a catch here, and so this is only, I mean, you can only revert this. So irrotational implies gradient field. If the domain of f is simply connected. So simply connected, let me just write it down. Let me just write down here, so simply connected. So SC, that's called simply connected. And this means kind of no holes in 2D. 2 dimensions, it means no holes. This is something we are looking at a little bit next week or so, why this is the case. And also a little bit the notion of simply connected. You explore this a little bit in the homework. This is a little bit of topology. Just a hint of topology here. Okay, I told you in class that we got recently solar panels on the roof for energy, so that we can produce energy also. But it's actually not true. We have even a much more efficient power supply. This is a secret of the Knill lab. So this is one of these perpetual motion machines. These are machines which generate energy out of nothing. And this is another one here. You might think this is a heat engine, Stirling engine type of thing. No, this is a perpetual motion machine. It produces energy out of nothing. So here is the machine. So what we have is a tube which is filled half with water. There are valves which make sure that the water doesn't go down here. And what we have is well known is we have a gravitational field, right, which pulls us down. And then we have also the buoyancy which pulls us up. If you put the wooden ball here in, so this is buoyancy. Or doesn't write buoyancy. So what we have, I had to look up buoyancy. So that's the buoyancy which pulls you up here. And so what happens is the ball comes down here, you see it here. And then the valve opens. Just show you that. So the valve opens when it is down. just show you again. The ball goes down, then the valve opens. Inside the water, it goes up, right? And then when it leaves on the top, you gain so much energy. You can make it so long that you gain so much energy that you can operate the valves. So that should be no problem. And you see when you open below, then the top is closed, so the water doesn't go out.
Which would keep pulling that side down, and the wheel would never stop turning. Without so much as a push, this wheel would spin forever.
So that's the thing. You find a lot of such movies, and actually a lot of fun to find the problem in it, or maybe there is no problem. Another thing which I kind of think is cool is you have magnets here. So you have magnets here. So you take a strong magnet, plus minus, plus minus, plus minus, plus minus, and you have a ball going around here. And this ball also is magnet, and it's actually plus minus like that. So what happens is this ball is pushed away from that and it's attracted here. When it comes here, the plus is negative here, it is pushed again, and it's pushed around. It's pushed around the whole thing. So that ball is moving around. So this is a magnetic perpetual motion machine.